A concept that's very closely related to work is that of power. And again, power colloquially means many, many different things, right? A powerful position or a powerful politician, someone who wields a lot of influence, or powerful stench, overwhelming stench. But power in physics is just the rate at which work is done. How quickly can you do work? That is your power. That's the power of the object. So power P is just the rate at which work is done, the change in work over time. How much work is done in a specific amount of time. Has SI units of watts. Now, many of you are familiar with the concept of watt because many of you use light bulbs, right? You buy a 75-watt light bulb or a 40-watt light bulb. Well, what does that mean? What is watt? Well, wattage is basically, again, how much power that light bulb gives off, radiant energy. How much work does it do converting electrical energy to radiant energy every second? So if you can quickly convert a lot of electrical energy into radiant energy over a short period of time, you have more power. You have a higher wattage light bulb. A 150-watt light bulb does more work, produces more radiant energy a second than a 4-watt light bulb does. Now, SI units of watts, so the power is work over time. Work has units of joules, right? Time is seconds. So 1 watt is 1 joule per second. Fairly easy. A joule is a kilogram meter per second squared over seconds. So watts, going back to the base SI units, is 1 kilogram meter squared per second cubed. Again, this is helpful if you need to worry about what units cancel. And the unit conversion sheet that I've given you access to has these base SI units on it. But the real conversion you need to know is here. Watts is a joule per second. Now watts, while it's common for light bulbs, and it's the SI unit for power, it isn't used everywhere. For example, a common non-SI unit for power is horsepower, especially when it comes to automobiles or motorcycles. Horsepower is supposedly comes from the idea of how much work can a horse do, right, in a second. Work being what, force can a horse apply over some distance every second. So 1 horsepower is equivalent to the power of 1 horse tilling a field. 2 horsepower is equivalent to 2 horses. Of course, horse is not a standardized unit of measure. They did have to standardize it to make the horsepower. Watt is a much better unit, a standardized unit. But 1 horsepower is about 746 watts if you need to do the conversion. And again, you think of horsepower. What does horsepower mean for a car? It means how quickly does that car accelerate, right? If you're in my first car, I think, has 80 horsepower. It was a 3-cylinder 1986 Chevrolet Sprint, I believe. A 3-cylinder had around 80 or 86 horsepower. It didn't really jump off the line during drag races. It went 0 to 60 in, my clock doesn't measure time that long, right? So 0 to 60 by the time you reach your destination. Whereas a drag race, 0 to 60 in just a few seconds. Because drag race cars have far more horsepower than, the sad little automobile that I had. They can do the same amount of work. My car will eventually hit 60 miles an hour. I think it topped out at 88. A friend told me that. But I stopped talking to him a short while after that. Sorry, getting off topic. It can reach 65 miles an hour or 60 miles an hour, but it takes much longer to do that. Therefore, it has less power than a sports car. Finally, another unit you might be familiar with is, remember, work and energy have the same units. So another way you can measure energy is how much power is given off by an object multiplied by time. Basically, you're solving this for work, and you're saying that the work done is equal to the energy brought in. So energy can be measured in units of power and time multiplied together. So if you've ever looked at your electrical bill, or your parents' electrical bill, grab it and look at how much energy is used. they bill you by what's called the kilowatt hour. They don't bill you by joules, the energy used by joules. And they don't care what the power is, right? They don't care how quickly you use the energy or how slowly you use the energy. You're billed by how much energy you use. But the kilowatt hour, watt is a unit of power. Kilo is a prefix of 1,000. So this is 1,000 watts, not per hour, but 1,000 watts times an hour. Well, an hour is not the SI unit for time. So you have to convert this to seconds. Kilowatts, you have to convert to watts. Watts times seconds is joules. So your electrical statement, you can actually do the conversion and figure out how many joules of energy did you use last month and what their billing rate is for that. However, kilowatt hour is the commonly used, it's an odd unit, but it kind of makes sense if you think about it. 1 kilowatt hour means that you burned 1,000 watts for an hour. So you have 10 100-watt light bulbs on for an hour, that's what you get charged for that. So it makes it a little bit easier to think about your energy generation, how often you use it during the day and so on, for savings rather than just having a unit joule, which might not make sense. Like watts, you measure your microwave, right? 1,700 watts, 1,400 watt microwave, or your oven might have watt ratings. Your amplifier, come listen to my stereo, it's 1,200 watts of power. Assuming you don't have your stereo cranked all the way up for an hour, or 1,000 such stereos, right? But if your stereo is 1,000 watts for an hour, that's how much you would get charged for using that stereo. So this is the concept of power. Again, it deals with how quickly energy is consumed or how quickly work is done on an object. Now, going back to your light bulbs, this is a little bit of an aside, but it's important. A lot of municipalities, a lot of countries are banning the use of incandescent lights. The old light bulbs we're all familiar with, less and less now as you get older, but as a child, the old school light bulbs. The reason they're being banned is because a 75 watt or 100 watt incandescent light actually produces very little radiant energy compared to the amount of thermal energy it produces. Maybe as a child you had an easy bake oven. I remember my sister had one that I probably ended up torturing Barbie dolls or melting crayons in at some point. The easy bake oven had a 40 watt light bulb with some foil on the inside. You put cookies in, and it was a small enough area and insulated enough that that light bulb would heat up the interior enough that the cookies would bake or the brownies would bake. Because most of the energy given off in an incandescent light is heat or thermal energy. Very little radiant, or at least visibly radiant energy from those light bulbs. So modern light bulbs are compact fluorescents or LEDs. Now, the problem though is when you look at an LED bulb, you might see an LED bulb is 10 watts. You're like, 10 watts? That's barely a nightlight. Why would I put a 10 watt bulb in my living room? But a 10 or a 20 watt LED bulb puts out as much visible light as a 75 watt incandescent. They just put out a lot less heat. So you'll see on the packagings for light bulbs, right, equivalent to a 75 watt incandescent, equivalent to a 150 watt incandescent, when really those bulbs put out far less power because they're more efficient at producing radiant light. And that's an advantage for physics because you're not spending money to heat your house with your light bulb. You're spending money to light your house with a light bulb. And that's what compact fluorescent bulbs and LED bulbs do far more efficiently. It's also why televisions are a lot cheaper to run today than they were in the past, because televisions use LED technology rather than the old cathode ray tube, which was very high power to generate the electron gun to light up your screen. So LED technology has come a long way at reducing power consumption and increasing lighting in the world.